Well, welcome to exponential functions, and I'm going to do a little introduction video here so that you can see what we're starting with. And I know you've seen exponential functions before, but we're going to get into depth and detail, and we're going to talk about growth factors and growth rates, decay factors and decay rates. So these two are basically the same, and we're going to talk about what the definition of an exponential function is. Okay, so exponential functions. Exponential functions represent quantities that increase or decrease at a constant percent rate. This is very important that you remember this, because if you hear the word percent per is the phrase, then you know automatically you're talking about exponential function. Okay? This is in contrast to linear functions in which a constant amount is added per unit. So for example, I would say this is growing 2% per year, and then the next year it grows 2%, and the next year it grows 2%, and so forth and so forth. Here I might add a number every year. So this could be like, oh, I'm adding $20 per year. Do you see the difference? This is an actual number that we're doing each time. This is an actual percent. Exponential functions involve multiplication by a constant factor for each unit. Examples in real life are savings accounts. They increase by percentages. The size of some populations. Populations are usually exponential growth because they grow quickly. And maybe a quantity of a chemical that decays radioactively. Okay, so when we talk about growing at a constant rate, so I want to make sure that you really understand this. So I'm going to start with a basic example. So linear functions are at a constant rate. Exponential change at a constant percent rate. This is important. Again, we're using the word percent per. So if you hear that, it's exponential. Let's start with an example on how this works. So say I had 60 bucks and I'm going to increase it by 20%. What would you do? Well, the first thing I would do is say I got 60 bucks. I'm going to increase it by 20%. So a percent I can write as a decimal, because this is divided by 100, as 0.2. So if I multiply 60 by 0.2, I'm going to get $12. Well, that doesn't mean that now I have $12. It increases by $12. So you actually have to take that $60, add the $12 we just found, and now I have $72. It's now been increased by 20%. Okay? An easier way to do this, so I'm going to say a little or here. So this is like two steps here. I've got step 1 right here and step 2. An easier way to do it is to take this and take the $60 and multiply it by 1.2, where the 1 stands for the 60 and the 0.2 stands for the 20%. If you were to put that in your calculator, you'd get $72 in one step. So you can do it the two-step way, or you can just multiply it by 1.2 and you'll get the $72. Now, I want to know, if I take and increase the 60 by 20% again, is this the same as increasing 60 by 40%? Because you're like, okay, if I did 20% here and then I do it again, that's 40%. Is it the same? Well, let's look. If I increase this 60 by 20% again, it's not 60 anymore, it's 72, isn't it? So I actually bring this down and say, okay, I'm taking that 72 because I increased it by 20% already. Multiply that by our shortcut way is 1.2, which is the 1 stands for the 72 and the 0.2 stands for 20%. I'd end up with $86.40 if I multiplied that out. The other way is, they said, is this the same as taking the $60 that we had originally and multiplying it by 40%? Well, let's do it by the shortcut way. I'm going to multiply it by 1.4, the 1 being for the 60, the 4 being for 40% of that. And when I do that, I get $84. Do you see how this is more? It's not the same. And the reason being is, after you take that 20%, when you take 20% again, you're taking it on a higher number. You're taking it with the 72. Excuse me, 72. So you're actually increasing it a little bit more because you're taking the second 20% on $72, which is a higher number. So no, they're not the same. You're like, okay, that makes sense. So let's practice a little bit what growing at a constant rate means. So I made this table. This is all percentages already. So this is 15%, 2%, okay? The decimal representation is we have to take, for percents, and we have to divide by 100, which, or you move 2 decimal places to the left. Because you're dividing it by 100. And the growth factor is either going to be 1 plus the rate or sometimes 1 minus the rate, depending on what the rate is doing. So the rate is always in decimals. So here's my rate right here. This is really my rate. And we're putting it, and this is a rate too. So this is the rate in percentage. This is the rate in decimal form. And then the growth factor, I have to do add that or subtract that, depending. So let's try this. So if I had 15%, multiply that, put that 2 decimal places to the left, that is 0.15 for decimal. And the growth factor is 1 plus the rate, so 1 plus 0.15 is 1.15. And you saw that earlier when we were doing that with the 20% thing. Okay, this is 2%. Move it 2 places to the left, that's really 0.02 for decimal. So that's 1 plus 0.02, or 1.02 is my growth factor. Ooh, I have a negative 30 here. So move it 2 places to the left, so that's a negative 0.30. Now, I have to do 1 plus the rate, but if you'll notice the rate's negative, so it really ends up turning into a negative. So when I do 1 minus 0.30, I get 0.70 because it's decreasing. I have a half here, which is 0.5. If I move that 2 places to the left, that'd be 0.005. So 1 plus 0.005 is 1.005. Negative 78, negative 0.78, 2 places to the left. 1 minus 0.78, because if I add the rate and the rate is negative, it turns negative. That comes out to be 0.22. Now I want you to notice a couple things. When this is growing, when this is a positive, do you see how my growth factor is over 1? Do you see how it's over 1? These two right here, this one and this one right here, notice my rate was negative. Look at my growth factor is between 0 and 1. So my growth factor is between 0 and 1. So it's going to be less than 1. It'll never be 0, but the growth factor is right in between those two. Okay, just so you know the pattern. This one is 100% growth, so if I move it 2 places to the left, it's a 1. So this is just a 1 for decimal representation, and then the rate growth factor is going to be 1 plus 1, or 2. So 100% growth factor really means you're doubling it. It's increasing. This one is 150% growth, so you go 2 places to the left, that's 1.50, and 1 plus 1.50 is 2.50. Okay, so that kind of gives you an idea of how those rates work. All right, let's do some actual examples so we can do this. And I'm trying to make these real life, so follow through with me and go through it with me so that you'll understand. So after graduating from college, you'll probably be looking for a job. Suppose you're offered a job at a starting salary of $40,000. Not bad. Per year. To strengthen the offer, the company promises annual raises of 6% per year. You see the 6% per year? So right now I know it's exponential for the first 5 years. All right? So if T represents the number of years since the beginning of your contract, and T equals 0 is when your salary is at $4,000, at the end of your first year, your salary would increase by 6%, and so forth, and so forth. So here I have a little graduating person all happy because they got a job. So let's look at the table and fill it in. Now I've already kind of graphed it a little bit to show you a couple things, but I want to do this with you. Please follow through with me, then you'll understand this. So here's year 0. Just got hired at your $40,000, okay? So what we want to do now is do our raise after the first year. So they told us we're going to get 6% raise. So if I get a 6% raise, I'm going to multiply by 0.06. When I do, my raise comes out to be $2,400. because that's what that is. So what's my salary at the end of year one? Well, if I add the $40,000 plus this, it comes out to be $42,400. So that's how much I make at the end of the first year. Now year two, I still get a 6% raise, but it's on the $42,400. So when I multiply that out, I get $2,544. Do you see how my raise every year is going up because I'm making more each year? So now at the end of the second year, I'm making $44,944. Now I want you to know I'm not using the cents, I'm rounding so that you can get the idea of this. So on and on, let's do year two. So I get a 6% raise because I'm a good employee. When I do, my raise comes out to be $2,697. So now after the end of year three, I make $47,641. It's a 4, everybody. I don't know why it's not writing. Okay, it's a 4. And then here I'm going to multiply this by 0.06. Okay, so when I do, my new raise is $2,858. And at the end of my fourth year, I break the 50,000 mark. I'm $50,499. Now, the reason why I did that is you'll notice these rates of increase are increasing. All right? The percentage is constant, so the percentage is constant. It's the constant rate. It's at 6%. Okay? It's a 6% constant rate. But if you'll notice, your rate is increasing each time I go down because the number's higher at the end of each year. So it's like I keep making more, so I'm taking a percentage of a bigger number. So this makes, if you were to look at this graph, it makes your slopes get steeper and steeper. So it curves because of that. So you get a steeper slope. And each time, and because you get a steeper slope each time, it causes this line to curve. And it curves very rapidly because look at, if you see here, after 4 years, I'm over $50,000. Right? Now, if I were going to try to make an equation out of this, we're going to talk about this later, but the equation would help because then I could always just plug in how long if I make 6% a year and what I would get. Right? All right, let's try decay one. So I have a radioactive decay one, which would mean it's decaying or declining. And I'm starting out with this carbon-14, and it takes about 1,000 years to decay 11.4%, which means there's less every 1,000 years. And we're going to start out with 200 micrograms of this sample. So it's going to decline each year. So as we go to do this, okay, we're going to kind of fill in all this stuff as we go along so you can see how it works. So again, this is declining every year 11.4%. So we start out with 200 micrograms, and I'm going to multiply it by 0.114. When I do, I get 22.8, and that means 22.8 micrograms are going away. So I take the 200, subtract the 22.8 micrograms. So after 1,000 years, I have 177.2 micrograms. Then the next year, I now have the 177.2, and that's decaying 11.4%. So I'm going to multiply that 0.114. So now 20.2 micrograms went away. So I take the 177.2, subtract the 20.2, and what's left over is 157 micrograms. Now I have that left. What I'm going to do now. So the first year I start out with 200 micrograms, so that's there. The second year I'm about 177, so that's about right here. And then the second 1,000 years I'm about 157, so that's about very much almost on that line there. Okay. And then the third year I have 157 micrograms, and I'm multiplying it by 0.114, and what I have taking away is 17.9, and I take the 157, subtract the 17.9, and I end up with 139.1 micrograms. So that's about right here, kind of. So if we were going to keep going, and I have kept going, and I even did up to 10,000, it's almost close to 50, you end up with this line, and I'm sure yours will look better, but it's actually curved, and it's going to keep going and going and going. But the one thing I wanted to show you is, now this one's decaying, see how it's going, and notice how steep the slope is, and then it's getting less steep each time, because if you'll notice, the amount that's decaying each time is dropping. So your slope is getting less steep. So again, your percentage is constant, which is 11.44%, but your slopes are less steep. Okay? All right, let's look at the formula here that we're going to come up with, and then we'll practice a few problems, and after this, I'll let you practice your homework. So in the book, if I had the quantity Q equals F of T, so my point would be TQ, and then they give you this formula, F of T equals AB to the T. Well, I have no problem with this, but we're going to do it this way. It makes it a little bit easier. So we have Y equals F of X, so the point is XY. So this is the way I would like you to do it. And then we're going to have you do it Y equals AB to the X. That's what I want you to use. Now, A is your initial value. It's kind of, and it's your y-intercept. And B is your growth factor. Now remember, your growth factor can be 1 plus the rate or 1 minus the rate. If it's over 1, it's growth. If it's between 0 and 1, it's decay, like I showed you that earlier. So we're going to be using this y equals AB to the x over and over and over again, because that is the formula. And notice you have a multiplication going on because we're talking percent per year. So let's practice the formula, and I actually put some of the formulas of the things we used before. This first one is the salary. So we're going to do the initial value of all these formulas, and we're going to do the growth rate. And it can be growth or decay if you wish. And we're going to use the formula y equals AB to the x. So all of these are in the form y. So this is the salary one. So our initial value is always A. It's in front. So our initial value here is $40,000 that we made. And if it's over 1, what you do is you take 1.06. You've got to get rid of the 1. Or lots of times I tell people just cover up the 1. If I subtract 1 from that, I get 0.06, which is 6%, and it's growth. So I'm putting an arrow moving up. So this is 6% growth, is what we had on that. All right. The next one, my initial value is always here, A, B to the x. So I have 67.38. And this is my growth factor, so I do 1.026, get rid of the 1, because I want to know what the rate actually is. Not the growth factor, I want to know the rate, so I get 0.026, move it back, so that's a 2.6% growth. So that's what the arrow means. Now, here are the ones that are a little bit tricky for people. So this one, my initial value is easy, that's 200. And the initial value of this one's 77. So that part is easy. But if you have something less than 1, you, instead of taking that minus 1, you're going to say 1 minus 0.886. All right? This means there's about 88.6% left. Okay? So I got to find what went away. That's what's left over. So when I do that, I get 0.114. Or 11.4%, and this is a decay. So anything less than 1, between 0 and 1, this is a decay. These two are growths. These two are decays. This one I'm going to do 1 minus 0.275. That's going to be 0.725. So that's 72.5% decay rate. So this means if this was per year, in this case it was every 1,000 years, it drops 11.4% per year. That means that's left over per year. This is the same thing. If 27.5% is left every year, that means 72.5% went away every year. Right. Let's practice some examples. And we'll finish up here. So if an account grows at 4.5% per year, so I know it's exponential, with an initial deposit of 500, what would your equation be? So I'd say y equals ab to the x. My initial value is 500, so that goes in the a spot, and then that part goes with there, so I have 500. And it's growing, so I know it's 1 plus my rate. So it's 1 plus 0.045 or 1.045 to the x. So you just came up with a formula for that word sentence. If an account loses value, so this is decaying at a rate of 5% per year, exponential, with an initial deposit of 1,000, I'll say y equals ab to the x. My initial value was 1,000. But this one's decaying or going away because I'm losing money. So when I subtract, I get 0.95. That's 0.95x. So that means 95% is left every year, and it's decaying. Okay. If B was 1.23, what's the value of R? So you take 1 minus your rate. All right, 1 plus your rate. So I'm going to say 1.23. I'm going to subtract the 1, so I have 0.23, or my rate is 23%, and it's growing. This one has my B as 0.80. What is the value of R? So I do 1 minus my rate, 1 minus 0.80, or 0.20, so that's 20% decay. Okay, I'm going to stop right here. There's a couple more slides that I'll do in class with you, but right there is the initial part of doing exponential functions.